Hello and welcome to the first video of the M3 chapter Kinematics. On the screen, M2 exam question to review this same chapter from M2. A particle P moves on the x-axis. The acceleration of P in the positive x direction at time t seconds is given by 2t minus 3. So we've got A is equal to 2t minus 3. The velocity of P in the positive x direction at time t seconds is v, and it does not start at rest. Here we've got the velocity is 2 when time is 0. Part A, find v in terms of t. So the review here is focused around the idea that we can find the velocity by integrating the acceleration with respect to time if the acceleration is a function of time. So we're integrating 2t minus 3, and that will give us t squared minus 3t plus c, and then our boundary conditions here, t equals 0, v equals 2, gives us c equals 2. So we've got t squared minus 3t plus 2. That's part A finished. The particle is instantaneously at rest, so v equals 0, at times t1 and t2. Find the values of t1 and t2. So we are finding when our velocity, which we know is t squared minus 3t plus 2, is equal to 0. So we factorize this, and we get t minus 2, t minus 1, and we know t2 is the bigger one, so t2 here is equal to 2, t1 is equal to 1. Part C, find the distance travelled between t1 and t2. Part C, we're now using displacement, and you can use x or you can use s. These are the two common variables to use for displacement. I will use s. And that is equal to the integral of v dt, where v is a function of time. So s is equal to the integral of t squared minus 3t plus 2 dt. And I'm not going to find a constant of integration because we're going between t1 and t2, so instead I can use the limits here, 1 and 2. So if we integrate this, we get t cubed over 3 minus 3t squared over 2 plus 2t, and we're going from 1 to 2. 2 cubed over 3 minus 3 times 2 squared over 2 plus 4 minus 1 cubed over 3 minus 3 over 2 plus 2. And that gives us an answer of minus 1 over 6. But don't leave that there because it wants the distance, not the displacement. So the distance should always be positive, 1 over 6 meters. And that's our final answer. If all of that is familiar to you, this first video should be fairly straightforward because it's basically just a review of acceleration varying with time. Maybe your integration or your differentiation will be a little bit more complicated in M3, but it's basically the same thing. In the next video, we go into acceleration varying with displacement. So in this chapter, we apply differentiation and integration to functions varying with time. Given displacement, you can differentiate that. So if you've got s, you can then find v by doing ds by dt, where s is a function of time. And then you can differentiate v to find a. And you can do this backwards by integrating. If you know a is a function of time, then you can find v by integrating a. And you can find s by integrating v. When you're integrating, don't forget your constants of integration, very important in this chapter. A particle P starts from rest at a point O and moves along a straight line. At time t seconds, the acceleration of P is given by this. Find the velocity of P at time t seconds. Okay, so we're going to do pretty much what we just did in the starter, and we're going to integrate the acceleration to find the velocity. Here we have 5 t plus 3 to the minus 2, and we can integrate this because the function inside the bracket is a linear expression, so we can just increase the power and divide by it. We get minus 5 t plus 3 to the minus 1 plus c. Now we're told it starts from rest, so when t equals 0, that's when it starts from rest, that's v equals 0. It also says at a point O, and if we're moving from O, then s is also 0 at that point. So these make up our boundary conditions. So if we know t is 0 when v is 0, that gives us a 0 here. And this is 3 to the minus 1, so that's 5 over 3. So c is equal to 5/3. So we get minus 5 t plus 3 to the minus 1 plus 5 over 3. This is the velocity of p at time t. Now we need to find the displacement of p from O when t equals 7. So first of all, we need the formula. So we need to integrate again. Put in the boundary conditions and then use t equals 7 to find out the displacement. So here we've got the integral of minus 5 t plus 3 to the minus 1 plus 5 over 3 dt. This first one will give us a log, so minus 5 natural log t plus 3 plus 5t over 3 plus another constant of integration. And again, when t is 0, we know s is 0 from that first sentence. So we get minus 5 log 3, and the next term is 0 plus c, so c is 5 log 3. S is equal to minus 5 log of t plus 3 plus 5t over 3 plus 5 log 3. And when t is equal to 7, which is what it actually wants in the question, we get minus 5 log 7 plus 3 is 10. And then a 7 here gives us 35 over 3 plus 5 log 3. And we could tidy that up a little bit by putting our logs together. We get 35 over 3 plus 5 log 3 over 10. Second example. A particle p is moving along the positive x-axis. At time t seconds, the velocity v of p in the direction of increasing x is given by this sine function. Initially p is at O. That word initially means when t is equal to 0, p is at O, so that's s is equal to 0. Find the magnitude of the acceleration of p at t is equal to 2/3. So we need to know the acceleration. We've been told the velocity, so here we are going to differentiate. Differentiating our sine function, we get a cosine function, and we pull out the 2 pi. So that gives us 10 pi cosine of 2 pi t. Now to find the magnitude, we just need t is equal to 2/3 and check that it is positive. 10 pi cosine of 4 pi over 3. That is minus a half, which gives us minus 5 pi. So it is negative, but if we want the magnitude of this, then we need to make it positive, and we get 5 pi meters per second per second. Part B, find the greatest distance from O reached by P. Now if we want the greatest distance, we're going to need to find the displacement formula. And again, to do that, we're going to integrate our velocity formula. So the integral of 5 sine 2 pi t, and that gives us minus 5 over 2 pi cosine 2 pi t plus c. This is the formula for the displacement, Now we have our boundary conditions here. So when s is 0, t is 0, cosine of 0 is a 1, that's minus 5 over 2 pi plus c. So c is 5 over 2 pi. So s is equal to minus 5 over 2 pi cosine 2 pi t plus 5 over 2 pi. Now to find the greatest distance from O reached by P, I want to know what is the biggest value this can take. And we know that the biggest value cosine can take is a 1. But in this case, that would make a negative here and a positive here. They would make a 0 altogether. So then if I want the greatest value of s, I'm going to need this to be a minus 1. So that this minus interacts with the minus 1, and we end up adding these two terms together, which would give us 5 over pi. So in this case, the greatest displacement, and if I take the positive, then that's the same as the greatest distance. So the greatest displacement is when our cosine term equals minus 1. And I don't even need to worry about saying when that happens, I just need to know s at that point is 5 over 2 pi plus 5 over 2 pi, which is equal to 5 over pi meters. And that is the greatest distance reached by P. Third example. A particle P is moving along the x-axis again. Initially, P is at O. So that's our boundary condition. When t is 0, s is also 0. At time t seconds, the velocity v of p in the direction of increasing x is given by this beast here. Now this is two functions. We've got 2t from the time 0 to 2, and then after 2 seconds it changes to 2 plus 4 over t. So we've got two functions, and our critical time is t equals 2. That's when we change from this one over to this one. Sketch a velocity time graph to illustrate the motion of p in the interval 0 to 5. Okay, so we've got our velocity time graph. Initially, that's very easy. From 0 to 2 is 2t. So let's put on all of our key values here. When t is 2, this is 4. Starting at 0, 0. This is velocity. This is time. After t is 2, we change to 2 plus 4 over t. That looks something like this. And you can see that this will never get smaller than 2 because t will always be positive. So we've got 2 plus something that gets ever smaller. So we've got an asymptote at 2. I'm not going to put that on though, because what it wants is from 0 to 5, and at t is equal to 5, we don't get that close to the asymptote to show it on the graph. You could, but I'm not going to. What I'm going to do instead is have that key point here and put on the value of v at that point. So when t is 5, that gives us a 4 over 5. 2 plus 4 over 5 is 2.8. And if you were to continue this, as I said, it would get closer to an asymptote at v equals 2. Part B, find the distance of P from O when t is equal to 5. So what I would normally do is to say, okay, displacement is equal to the interval of v dt, and work that out and put in t is equal to 5. And that would work, except in this case you've got two functions to integrate, and you would have to put in t is equal to 2 here first, and then for this one you would have to go from 2 to 5. You can kind of get around that a little bit by remembering the area under your velocity time graph is equal to the distance traveled. So an alternative way of doing this one is to calculate this area here, and I'm sure immediately you're thinking to yourself, well, that means we're going to have to integrate, and it does. But we only really need to integrate this S2 region here, because over here we've got a triangle. It's very easy. We can just do 4 times 2 divided by 2 there to give 4. So from 0 to 2 it travels 4 meters. Now for S2 we will have to integrate 2 plus 4 over t, and it will have to be from 2 to 5. Then I'll add these two regions together, and that will be the total distance of p from O when t equals 5, because you can see from the graph that there's no negative velocity. We're not going backwards at any point. Integrating this gives us 2t plus 4 log t, and we're going from 2 to 5. That is 10 plus 4 log 5 minus 4 plus 4 log 2. 10 minus 4 is 6. And if we take out the 4 there, we can combine our logs. Log 5 minus log 2 is log 5 over 2. Now to get our total distance, we add s1 plus s2, and that gives us 10 plus 4 log 5 over 2. And there is our total distance when t is equal to 5. Final example. A particle p is moving along the positive x-axis again. At time t seconds, the velocity is this. When t is equal to 0, p is not at the origin, but 10 meters from the origin. Find the values of t when p is instantaneously at rest. So again, we're starting off with this v equals 0, and we need to find what is t. So 2t squared minus 7t plus 3 equals 0. Factorizing that gives us a 3 and a 1, minus, minus. So t is equal to a half, or t is equal to 3. Part B, find the displacement of p from O when t is equal to 5. So to find the displacement, we need to integrate the velocity. So we're integrating 2t squared minus 7t plus 3, and that gives us 2 over 3t cubed minus 7 over 2t squared plus 3t plus c, and when t is equal to 0, each of these three terms are 0. P is 10 meters from the origin, so s is equal to 10, so c must equal 10. So our formula here is 2/3 t cubed minus 7 over 2t squared plus 3t plus 10. Now we just substitute in when t is equal to 5, and that gives us s is equal to 250 over 3 minus 175 over 2 plus 15 plus 10, which is 125 over 6 meters. Find the total distance travelled by p in the interval from 0 to 5. Now we have to be a bit careful here because we want the total distance, not the displacement when t is equal to 5. We've already got that. So what's happening here, we've got the origin, say here. We're starting off 10 meters away, and then it's travelling. It ends up much further away by t equals 5, but it does it in stages. So maybe, for example, it goes up to here when t is equal to half, and then maybe it goes back down here when t is equal to 3, and then it goes back up here by the time t is equal to 5. And the total displacement from the origin at t is equal to 5 is this. The total distance would be this, plus this, plus this. So we need to find each of these little pieces here. So what we're going to do is to do this in parts. We're going to start with t is equal to a half, and that gives us s is equal to 257 over 24. Now that's the displacement again, so we want the distance travelled from here, which is where it starts, to here. So the distance travelled is this minus 10. So to get the distance here, 257 over 24 minus 10, 17 over 24. But that's just the first stage. Now from t is equal to a half to t is equal to 3, we need to know the next point, and that gives us s is equal to 11 over 2, or 5.5, and you can see that this is bigger than this, so it has come back on itself. To To find this distance, then we need this point minus this point. So 257 over 24 minus 11 over 2. Call that distance 1. Distance 2 gives us 125 over 24. And then our final part, we've already got the numbers. We know that when t is equal to 5, the displacement is this. And we're coming from here, which is 11 over 2. So distance 3, this one is this minus this. And that gives 46 over 3. So the total distance is, adding all those three together, 85 over 4 meters, or 21.25. And that is the final answer of the final example. You can now attempt questions from exercise 1A, and maybe I'll see you in the next video.